So this is the first tutorial on induction motor, three-phase induction motor, tutorial 14th, and we are going to solve few questions on it. So problem number 1, a 4-pole three-phase induction motor operates from a supply whose frequency is 50 Hz. So the number of poles given is 4 and the frequency is three-phase 50 Hz frequency. What is the speed at which the magnetic field of the stator is rotating? So basically we need to find what is the value of ns. So ns is the speed of the stator magnetic field. So the speed at which the rotor is rotating when the slip is given to be 0.04. So this is the value of the slip given and you have to calculate what is the value of NR. The frequency of the rotor current when the slip is 0.03. So what is the frequency of the rotor current that is under the running condition? The frequency of the rotor current under the standstill condition. So standstill condition means the motor is under stop. So what is the value of the frequency of the rotor current? So let us see the solution. The first point that we have to solve is what is the value of the synchronous speed. Synchronous speed is the speed at which the field is revolving. The formula being given as ns is equal to 120 f by p, where f is the frequency of the supply and p is the number of poles. Here the frequency is given to be 50 Hz and the number of poles is given to be 4 and the constant is 120. So on solving you will get 1500 rpm. The unit of the speed we calculate in rpm. Second, what is the rotor speed? So the function formula for the rotor speed is nr is equal to ns 1 minus s. So here s being the slip. So at a particular slip you will get one rotor speed. So when you change the slip you will be getting a different rotor speed. The synchronous speed remains the same, which we have calculated as 1500 rpm. So on substituting the synchronous speed as 1500 rpm and the slip given to be 0.04, we will getting the rotor speed as 1440 rpm. In induction motor, for every cases we will get NR value is always less than NS. So the speed of the rotor will always be less than the speed of the synchronous speed. Now, what is the frequency of the rotor current? So when the slip was 0.03, what is the frequency of the rotor current? So basically the formula for the frequency under the running condition is equal to slip time the frequency of the supply. So frequency of the supply being given to as 50 Hz and the slip given to be 0.03. So at this particular value of the slip, what is the frequency of the rotor current? So we have to multiply the slip with the frequency. So frequency is 50 Hz. So we are getting a frequency of the rotor current as 90 rpm. Next, at standstill condition, what is the value of the frequency of the rotor current? So standstill condition means that the value of the slip will be 1 because the rotor is stopped at this particular point. When slip is 1, you will be getting the formula under the running condition f dash is equal to slip time frequency. Since the rotor is standstill, the value of the slip is 1 multiplied with the supply frequency, which is 50 Hz. So at standstill condition, the frequency of the supply is 50 Hz. So this is the frequency of the rotor current. So we find that at the running condition is equal to supply frequency when the value of the slip is 1 or the standstill condition. So this is the first problem. Next problem, we have a three-phase induction motor having a star connected rotor. So when you have a three-phase system, then you will be having a different connection for a stator and the rotor. Here you have been given that star connected rotor, which has an induced EMF of 80 volts. So induced EMF means the value of the E2 is given for the rotor between the slip rings at standstill condition on open circuit. The rotor has a resistance and the reactance per phase. So whenever we have a three-phase induction motor, the parameters of the induction motor, that is the resistance and the reactance, will be given per phase basis, that is 1 ohm and 4 ohm respectively. Calculate the current per phase and the power factor under the two different conditions. One is when the slip rings are short circuited and when the slip rings are connected to a star connected rheostat of 3 ohms per phase. So slip rings are short circuited basically means that we are basically operating on squirrel cage induction motor, and when it is connected to a rheostat of 3 ohm per phase, basically we are operating on phase mount motors. So let us see the solution. So at the standstill condition, the rotor EMF per phase that we have to calculate. So here in this problem, 80 volts whatever is mentioned, that is corresponding to 3 phase, and we have to solve all the problems based on single phase. So we have to divide it with the root 3 so that we get as 46.2 volts. Now the first condition was that the slip rings are short circuited. So what is the rotor impedance Z per phase? So we know that the value of impedance is equal to under root R square plus X square. So the resistance being given to be as 1 ohm and the reactance given to be as 4 ohms. So we get 4.12 ohms as the rotor impedance. This means that the current that is flowing in the per phase, so we need to find the current. So current is basically what is the amount of the voltage divided by the total impedance. So voltage we have already calculated as 46.2 and the impedance is equal to 4.12. This gives the current to be 11.2 ampere. Now power factor, which is the cosine of the phase angle between the voltage and the current, we can calculate with the knowledge of the value of the resistance and the impedance Z. So here the resistance being given to be as 1 and the impedance we have calculated as 4.12. So it means that the power factor cos phi is equal to R by Z. We get 0.243. At a low power factor, the starting torque will also be low. So we know that when slip rings are short circuited, you do not have the provision to connect an external resistance. In that case, the power factor, if you observe, it is quite poor, and then the starting torque will be very low. Now, when slip rings are connected to an external resistance through a star connected rheostat, so the rotor resistance has now increased. So we have a resistance of 3 ohm which will be added to the existing 1 ohm, so it becomes 4 ohm resistance. Now impedance we can calculate as under root of R square plus X square. So here R new will come because we have calculated 4 ohms as the new resistance when you have a rheostat connected. So this gives the value 5.66 ohms as the impedance per phase. So current, similarly we can calculate the value of voltage by impedance. The voltage being 46.2, which is constant, we have calculated, and the impedance we have calculated as 5.66. So this gives 8.16 as the rotor current per phase. And the value of the cos phi, that is R by Z, here R is basically 4 ohms and the impedance we have calculated as 5.66, that will give you 0.707. So compared to the previous case, we have seen here that the power factor has improved a lot. So starting torque can be increased with the improvement of the power factor. The power factor is improved by adding more resistance to the circuit using the rheostat, so that the value of the cos phi become better. So here we can see that cos phi has become better compared to the previous case, so that the starting torque is increased. The third problem, you have a 3-phase 400 volt star connected induction motor has a star connected rotor with a stator to rotor turns ratio given 6.5. So similarly in a transformer, we know that the transformation ratio in the transformer is equal to N2 by N1 where N2 is the number of turns in the secondary winding by number of turns in the primary winding. So here the 2 will become your rotor and 1 will be your stator. So here the information of the stator to rotor turns are given to be 6.5, which can be used to find the transformation ratio. The rotor resistance and standstill reactance, the value of R2 and X2 are given per phase as 0.05 ohm and 0.25 ohm respectively. What would be the value of the external resistance per phase to be inserted in the rotor circuit to obtain the maximum torque at the starting? So you need to find the maximum torque at the very start. Then what is the amount of the extra resistance that you can add with the rotor circuit, and what will be the rotor starting current with this resistance? So what is the value of the current here? So that is the problem third. So let us see. Now let us find first the transformation ratio similarly to in transformer, which is rotor turns by stator turns, and this calculation will be done per phase basis. So it will be 1 by 6.5, which is given to us. Then the standstill rotor EMF per phase. So we have been given as 400 volt 3-phase induction motor. So if we divide with root 3, we are getting per phase, and that we are getting the value of E1. So we can calculate the value of E2 is equal to K times E1. So K is basically the transformation ratio, which we have got 1 by 6.5. So this is your transformation ratio, and 400 by root 3 is basically the per phase induced EMF in the primary voltage, primary supply or the stator turns. So we are getting 35.5 volts as the rotor EMF per phase. Now we know the condition that where the starting torque will be maximum when the rotor resistance and standstill reactances are equal, and this will be given condition 0.25. So R2 has to be equal to X2, which is given as 0.25 ohms. So it means that the external resistance that has to be added per phase is basically 0.25 minus the resistance which is already given for the rotor circuit. So this comes to be 0.2 ohms. Hence the rotor impedance will be under root of R square plus X square. So we have got that the value of the resistance as 0.25 and the value of the reactance is also 0.25, because we have to obtain the maximum torque condition. So this gives the impedance to be 0.3535 ohms. So the current basically is equal to the voltage divided by the impedance, and the voltage 400 by root 3, which is your, you have got multiplied with the transformation ratio, you got 35.5 in the rotor circuit. So 35.5 volts divided by the total impedance, which is 0.3535 for the maximum torque condition, we get 100 ampere approximate. So problem fourth, which is the last problem for this particular tutorial. So let us see, we have a 1100 volt 50 hertz delta connected induction motor. So here you have a delta connected, has a star connected slip ring rotor. So this means the delta connected is basically the stator and the star connected is basically the rotor. And the phase transformation ratio, so here the term phase has been used, which is 3.8. The rotor resistance and standstill leakage reactances are given to us as 0.012 and 0.25 ohm per phase respectively. Neglecting the stator impedance and magnetizing current, determine the rotor current at the start with the slip ring short circuited. So what is the value of the rotor current at the standstill condition? The rotor power factor at the start with slip ring short circuited. So what is the value of cos phi 2 when the rotor is standstill? The rotor current at 4% slip. So when the slip is 4%, what is the value of the rotor current? Now I2 dash. The rotor power factor at 4% slip. So what is the new value of the power factor cos phi 2 dash? The external rotor resistance per phase required to obtain a starting current of 100 ampere. So you need to find what is the rotor resistance you require per phase to maintain the starting current as 100 ampere in the stator supply lines. So you have a 1100 volt and this is corresponding to 3 phase. So we have to find these particular parameters for the 3-phase induction motor. So let us see the solution. So first we know that the connection is basically delta star connected induction motor. So these relationship will be required to find the voltage and the impedance. And the transformation ratio has been given as 1 by 3.8 because the stator to rotor is given. So you need to find the rotor to stator per phase transformation ratio K. So that gives you 1 by 3.8. Now the rotor phase voltage at standstill condition, so this is the value of E2 that you need to find, is equal to the transformation ratio K multiplied with E1. So since the stator is delta connected network, so we know that in delta connection the line voltage is equal to phase voltage for a delta connected network. So 1100 volts, which is the stator voltage, will be same whether it is for the line voltage or for the phase voltage, multiplied with the value of the transformation ratio will give you the value of the induced EMF E2 at the standstill condition, which comes to be 289.5 volt in the rotor. Now the rotor impedance Z that we need to calculate is equal to R square plus X square. So given the values of the resistance and the reactance, we can calculate what is the value of the impedance of the rotor. Then the current, phase current at the starting. So at the starting the current will be voltage divided by the impedance. So standstill value of the voltage is 289.5 volts. This is at the standstill condition. So 289.5 divided by the total impedance, that is 0.2503, we get a phase current of 1157 ampere. And the power factor at the standstill condition, start condition, is basically the total resistance by the total impedance. So resistance is given to be as 0.012 divided by the impedance of the network, which we have calculated 0.2503. So it is 0.048 in the lagging condition. Now that calculation are all in the when that is in the stopping condition. Now at 4% slip, so the value of the slip is basically 0.04. The value of the rotor reactance, now resistance will be constant, it will be irrespective of the speed of the machine, but the reactance will change. So this will be slip time the standstill reactance. So standstill reactance was 0.25. This is the value of x2, and this is the slip wedge at which we need to calculate what is the reactance. So this gives to be 0.01 ohms. Now the new impedance under the running condition will be equal to under root of R2 square plus the XR, that is the running condition square. So this is the new value of the reactance which we have to substitute in the value of the impedance to get the new impedance as 0.0156 ohms. Similarly, the induced EMF in the rotor circuit is equal to S into E2. So 289.5 is under the standstill condition. So under the rotating condition, you have to multiply it with the slip. So that gives you 11.58 volts. So the current is basically the voltage by impedance. The new voltage induced EMF we have find out as 11.58 and the new impedance is 0.0156. So that gives you the current as 742.3 ampere. So the new power factor at the value of 4% slip is basically the value of, what is the value of R by Z. So the resistance is constant, which comes to be 0.012 divided by the total impedance, that is 0.0156. So we have to divide this, that will give you the new power factor as 0.77. Now, what is the current that is flowing in the rotor circuit I2 is basically we will find from I1 by K, because we know that the transformation ratio K is basically N2 by N1 is equal to I1 by I2 is equal to V2 by V1. So these relationship of the transformation ratio we can use to find the value of the current flowing in the rotor circuit I2 is equal to I1 by K. So we have obtained the value of I1, which is 100 ampere. It is given in the problem, multiplied with 3.8 because it is 1 by K. So 1 by K is 3.8. So multiplied with 3.8, you get 380 ampere is the current flowing in the rotor circuit when the supply line has to be kept fixed at 100 ampere. So the E2 value at standstill condition is already we have calculated as 289.5 volts. Then the impedance Z2 is equal to the voltage divided by the current. So voltage is in the standstill condition is 289.5 divided by the new value of the current, that is 380 ampere, I2 in the rotor circuit, that gives to be 0.7618 ohms. Hence the resistance R2 is equal to under root of Z2 square minus X2 square. So Z2 we have calculated as 0.7618 minus the reactance 0.25. So the resistance we are getting 0.7196. Hence the final thing that we have to obtain is what is the external resistance required. So this is the resistance 0.7196 which we require to produce a current of 100 ampere minus the total resistance which is already given in the rotor circuit. So that gives you 0.707. So this is the resistance which has to be incorporated in the rotor circuit so that 100 ampere is maintained at the supply line. So this complete the tutorial fundamental problems on induction motor.